So here we will be discussing about how to evaluate the primary consolidation settlement and as well as the secondary consolidation settlement. So first part we will see about the primary consolidation settlement. So for that I consider the soil skeleton, and since it's an assumption that the soil is remaining fully saturated at at any case of the consolidation, at any stage of the consolidation. So this is particularly the soil solid, this is the water. The soil is fully saturated, so therefore there is no as such air voids. I consider the volume of the solid as unity. Since I have considered the volume of soil solid as unity, this will become equal to void ratio E, that is the volume of the water, and the 1 plus E will become equal to V total V, right? Because I've considered it as a unit quantity, and therefore what happens while application of the load, once you have applied the load, the volume will be changing or volume will be decreasing, and this would be the change in the void ratio delta E, and this is the initial level, and the soil solid volume will be remaining it as same. There won't be any kind of the change in the volume of the soil solid. So therefore I'll consider that the change in the volume to the original volume as a factor, which is nothing but the volumetric style. So this became, since in this formulation I considered the area to be unit meter square, which is perpendicular to the plane of paper. Therefore volume will be this particular expression is reduced in terms of the thickness of the soil layer, which is delta HYH. So if I want to calculate this particular change in the volume to the original volume, I need a certain kind of the formulation. So that formulation we did it in the one dimensional consolidation theory in the Terzaghi, that we have seen the equations like the E, which is equal to volume of void divided by volume of soil solid, and also we have seen there that the volume of so in this equation, if I just add 1 to the both side, you will get it equal to total volume by Bs as 1 plus E. And also we have seen the expressions like so if I just place the Vs equal to V divided by 1 plus E in this expression of E, which is equal to Vv by Vs, so we'll get the E at any stage, because we have considered the initial void ratio in this for deriving this particular example. So E at any stage of the consolidation will be equal to the volume of voids divided by volume of soil solid, and I need to place volume of soil solid as V divided by again 1 plus E. But remember, whatever change in the void ratio will be happening, the change is happening only in the voids. There will be no change in the solid volume. So therefore, delta A will become equal to delta VV divided by the total E. So therefore, delta VV divided by V will become equal to delta E divided by 1 plus E naught. See here, it's 1 plus E naught. It's an initial void ratio. So this is one expression to get the settlement value with respect to the change in the void ratio. So this is the delta H. So we will be using the same expression in the henceforth coming derivation, which is equal to delta E divided by 1 plus E naught. Since we know that the coefficient of the compressibility, that is nothing but the AV, this is remaining constant. That's what our assumption is, and this particular AV is nothing but delta E divided by delta sigma dash, and we did it in your EP curve, or I call E sigma dash curve. So this particular curve we have seen like this way. We consider that this particular curve is relatively a straight line, the slope of the virgin compression part is nothing but AV. And from this particular expression, if I just place the value of delta A, which is AV into delta sigma, in this expression, you will get it as AV into delta sigma dash divided by 1 plus E naught. And again, if you recollect the definition of the CV, we have left it out the parameter like this: K divided by AV divided by 1 plus E naught into gamma W, and this particular parameter we referred it as a CV in that particular derivation, and we termed this particular parameter as the coefficient of volume compressibility as MV, and MV we call it as AV divided by 1 plus E naught. This is again very important expression, coefficient of volume compressibility. And from this particular expression, if I replace this in this equation, you'll get the same AV as the MV into delta sigma dash, and delta sigma dash is the change in the effective stress. Remember, this is very important. This is nothing but a change in the effective stress, delta sigma dash. And therefore, from this particular expression, you'll get it as delta settlement, which is nothing but the change in the thickness of the soil layer, equals to MV delta sigma dash into original or the initial height of the soil specimen. Right. So this is again one more expression to evaluate the settlement of the soil. And one more expression we'll see in this aspect is which is related to the compression index of the soil, CC. And in many cases, the compression index of the soil is empirically related to the liquid limit, which is as follows: CC equals to 0.009 liquid limit minus 10%. And this particular expression is used, it is given by Terzaghi and Peck. Peck is the student of the Terzaghi. Terzaghi is obviously the father of the soil mechanics, and it is given by the Terzaghi and Peck, and this is used for the clays which has the sensitivity value less than 4. ST is the sensitivity value. And we have seen the definition of the sensitivity in the index properties of the soil. The definition is as follows: the unconfined compressive strength of the soil when it is at the undisturbed state to the unconfined compressive strength of the soil when it is at a disturbed state. So just it is the strength at undisturbed to the strength at the disturbed state or the remolded state. So this particular is the empirical expression, and various scientists have given the empirical relationship related to the liquid limit, plasticity index, IP, and the natural water content at the present which is present in situ of the clay. But we are not concerned about this particular part. We are just concerned about the computation of the settlement. So as you are aware that if the soil is normally consolidated, then if you just plot the graph of log of sigma dash versus the E curve, you will get a straight line for normally consolidated soils. This is for normally consolidated soils. And the slope of this particular part we termed as the compression index, CC, and therefore from the definition, CC will become equal to delta E divided by log to the base 10. We'll get hopefully, so if I just take the two values, this is the initial E1, this is final E2, this is sigma 2 dash, sigma 1 dash. So you'll get it as sigma 1 dash divided by sigma 2 dash. Alright, sigma 1 dash divided by sigma 2 dash you will get. And also if I just take, this is the increase in the stress or because of the loading delta sigma dash, then Cc will become equal to delta E divided by log to the base 10 into sigma 2 dash plus delta sigma dash divided by sigma 2 dash. This is again the same expression, and we'll place this particular expression of the Cc in your original existing equation, which is delta H by H becomes equal to delta E divided by, this is the original equation, 1 plus E naught. E naught is the initial void ratio, so therefore the settlement, ultimate consolidation settlement, delta H will be equal to CCH divided by 1 plus E naught into log to the base 10 sigma 2 dash, which is the previous stress, plus the increase in the stress delta sigma dash divided by previous stress that the soil is experiencing. Obviously you need to place everything in the effective stress parameters. So this is the final expression which gives the ultimate or the final or ultimate primary consolidation settlement. So this particular value of the final ultimate consolidation settlement is at u equal to 100%. That means at the 100% of the, we said that this particular settlement is occurred, that means 100% primary consolidation is being achieved. So this is at 100% degree of the consolidation. But if you recollect here in this equation is that the ultimate value of the consolidation settlement is depending on the thickness of the specimen, soil properties, initial as well as the compressibility characteristics of the soil properties, and also it is very much dependent on the increase in the stress levels. But now you can ask me that where is the time in this equation? So time is not reflected. But remember, time and the degree of the consolidation, u is affected, and which is by Tv equal to Cv T by D square value. So here there is a time factor, and here it's a MV, CV value, and CV is again related with the MV parameters like this, K equal to CV MV gamma W, and this MV is related to the AV. So AV equal to MV into 1 plus E naught, and AV is obviously will be directly or indirectly related to the compression index. So that's how it's everything is linked, right? So this particular part we have seen it for the normally consolidated soils. We'll see for the over consolidated soil. That means the primary consolidation in over consolidated soils. Primary consolidation settlement in over or pre-consolidated soils. So as you are aware that the pre-consolidated or the over-consolidated soil, which means that the plot of E versus log of sigma dash up to the pre-consolidation stress is like this, and then after it gets like this. So this is the field curve, and we also saw how to transform lab curve into a field curve by Smirtman method we solved in our previous lectures. So therefore this particular part, which we call it as virgin compression part, this is virgin compression, and this is the recompression part of the curve, and the slope of the recompression part we call it as CR, and the slope of the virgin compression part we call it as the CC, that is compression index. And this particular point from where the two distinct zones have been separated, the pressure corresponding to this point we call it as the pre-consolidation pressure, sigma P dash, or you can call it as sigma C dash anyway. But in order to calculate the, let's suppose this is the initial word ratio E naught, but if you want to calculate the total settlement at the pressure which is greater than the pre-consolidation stress, then the story, everything story will change. So now I'll bring out the formulation, but remember in this formulation it depends on your existing stress levels. If you have got the existing stress levels less than the pre-consolidation stress, then you will be using only this particular slope value into consideration. So for the first case, what I will be considering that your existing stress sigma existing stress, effective stress, is less than the pre-consolidation stress sigma P dash. Then the settlement will be equal to, just you need to replace it with the CR value with the previous equation. You need to replace CC by CR. CC is the compression index which is experienced by the normally consolidated soil, which means the virgin compression. This is applicable for virgin compression part of the EP curve. This is CR into H divided by 1 plus E naught into log to the base 10. The same way, if you have got this particular existing pressure sigma dash E, so this becomes like sigma P dash, because it's changing from E naught to this particular value. The stress is changing from this particular value to this particular, so there would be only change in this particular E value. So therefore it becomes sigma E dash, or sigma E dash divided by 1, I call it as divided by 1. What we have considered here is that the pressure initially existing is just the nominal, which is 1 or unity. So from this part to this part, the settlement occurring would be this much delta H. But from this part to this part, the settlement occurring will be corresponding to existing to this particular value. So second case, if you have got the existing pressure which is greater than the pre-consolidation stress, second part, sigma effective existing pressure greater than sigma P dash, then the settlement would be equal to CR into H divided by 1 plus E naught into log to the base 10. You have got the pressure existing like this. This is existing pressure, effective pressure in this region. So therefore from this to this you have got sigma P dash. So therefore from initial part, sigma P dash divided by sigma O dash. So O dash was the initial existing pressure. I'll again rewrite this one by sigma O dash. Sigma O dash was the initial pressure. Initially it was been or you can call it as a past pressure, initial existing, and this is the initial existing pressure sigma O dash, and somewhere sigma O dash will be lying like this, very close to the zero line. So this is sigma O dash, very near to the this particular vertical line, sigma O dash plus CCH to the 1 plus E naught into log to the base 10. See, you remember this particular one first part is from this to this. This is sigma O dash. Sigma P dash and sigma O dash is reflected by the slope of the recompression part, that is CR. But from this to this, that is sigma dash existing to the sigma P dash, there is CC part. So here it is sigma dash existing divided by sigma P dash. So this is that's how you'll calculate the settlement if you have got the existing pressure in recompression part, or whether you have got existing pressure in the virgin compression part of the curve. So it is very easy. First of all you need to find it out the initial existing pressure, and you need to correlate with the currently pre-consolidation and existing pressure, and based on that you can calculate the settlement. So this finishes the evaluation of the primary consolidation settlement. We'll briefly discuss about the secondary consolidation settlement and how to calculate. So if you recollect, our components of the total settlement, which is divided as immediate settlement, which is occurring immediately after the application of the load, and second part is the primary consolidation settlement, which is a very bigger part in case of the clay soil, and the secondary consolidation settlement, also called as the creep settlement, which is very important in case of the organic soils, and that particular settlement is calculated from the lab test. But for that you need to plot a graph of the void ratio versus the logarithmic of the time, because this particular secondary consolidation settlement is occurring at constant effective stress. And if you plot this particular graph, then you will get it like this way. The graph will be, and it will touch asymptotically. This is the initial void ratio for the commencement of the secondary consolidation, or this is the void ratio at the end of the primary consolidation, E, and this is the plot of the E with respect to time, but it is occurring very important at constant effective stress. Effective stress at this point is constant. So we'll define the angle slope of this particular curve at intermediate state by CS or I is equal to C alpha. In this particular C alpha becomes equal to delta E divided by delta log T. And once you get to know about this particular secondary compression index, C alpha is nothing but secondary compression index, which is not related to the change in the effective stress, it is related with time value. We can calculate the settlement as follows: delta H becomes equal to C alpha into H into delta log T divided by 1 plus E naught. Or here we call it as the final void ratio at the end of the secondary consolidation. So remember over here, the EF is the void ratio at the end of the primary consolidation. So therefore EF is the will come to this end, because from this void ratio the secondary consolidation is starting. So therefore it will be EF, which is the nothing but the final void ratio at the end of the primary consolidation, and from this point your secondary consolidation is starting. So many researchers have found out that the value of the compression index to the this particular C alpha, that is nothing but the secondary compression index. So there is correlation between these two parameters, and this ratio C alpha to Cc in most of the inorganic soils ranges between 0 to 5%. But for organic soils, the ratio of C alpha to Cc can go up to 11%. So there the secondary consolidation becomes very important. So in this aspect we finishes the computation of the primary as well as the secondary consolidation, and also we have seen that how to calculate primary consolidation with the change in the effective stress, and how to evaluate the creep, that is the secondary consolidation, which is occurring under the constant effective stress with the time. So this finishes the computation of the consolidation settlement. Thank you.